One of the terms you might hear when you talk about amplifiers is the common mode rejection ratio. In this video, I'm going to explain what that means. Generally, for an amplifier, for a good amplifier, you want the common mode rejection ratio to be a big number. Let's first look at a general amplifier, and I'll show you what I mean. Let's take a look at a block diagram of a simple amplifier. An amplifier generally sits between a small signal source and a load. The job of the amplifier is not only to amplify voltage or not only to amplify current, but generally to amplify power. What it means is that if an amplifier is working as designed, the voltage times the current at the input side will normally be less than the voltage times the current at the output side. What it means is that when we look at a block diagram like this, we're missing some lines. The current going into the amplifier is not necessarily going to equal the current coming out of the amplifier. So you can't, for example, apply the Kirchhoff current law to such a block diagram. What I'm showing here is a voltage amplifier. If you look at the equation, you'll see that I have the output voltage written as some constant, A sub V times the input voltage. A sub V here is just a constant, and this constant is dimensionless because the voltage at the output is measured in volts and the voltage at the input is also measured in volts. If this amplifier had been something other than a voltage amplifier, for example, if the output had been a current rather than a voltage, then A might not be unitless. It might have, for example, values of ohms or inverse ohms. For now, we're going to just concentrate on voltage amplifiers. Let's model our voltage amplifier to illustrate the fact that, for example, the Kirchhoff current law can't really apply. The amplifier here sits in between our input and output. The input impedance of this amplifier is given by R sub I. Since this is a voltage amplifier, we generally want this input impedance to be as large as possible. That's good because it uses less power from the source. The output impedance of this amplifier is given by R sub O. Since we nearly always want the output voltage to be a simple constant times the input voltage, and we don't want any drop from here to here, it makes sense for this output impedance to be as small as possible in a good amplifier. That is to say, in a voltage amplifier, we want to have a small output impedance. The constant A sub V is called the gain. In this case, it's the voltage gain. You might notice that our source over here at the left, V sub S, is drawn with a circle, but our source here inside the amplifier is drawn with a diamond. That's because it's a controlled source. It depends on some other source. In this kind of general amplifier that I'm showing right now, we have only one input. But there's another kind of amplifier that I'd like to introduce to you now, and that's one that requires two sources, a differential amplifier. The job of a differential amplifier is to subtract one input voltage from another input voltage and multiply that times some constant. The negative sign in this equation is why it's called a differential amplifier. The gain here has a subscript D to indicate that it's the differential gain. A good differential amplifier will have an output voltage that always follows this equation. There's something interesting about this equation that I'd like to highlight. If you increase V sub 1 by 1 volt and you increase V sub 2 by 1 volt, what's going to happen to the output voltage? It should cancel out. In other words, if we add some constant value to both V1 and V2, the output of the amplifier should not change. That would be a good differential amplifier. In other words, it only gives us some function of the difference between the two signals, and it doesn't amplify something that's common to the two signals. Let's look at this in a little more detail. I'm going to now define common mode and differential signals in order to make this analysis a little bit more complete. First, I'm going to look at just two voltage sources, V sub 1 and V sub 2. Relative to ground, the voltage here at this node is V sub 1, and the voltage down here at this node is V sub 2. I'm now going to introduce an equivalent model, but with different labels. I'm going to represent it by a single common mode source, CM here in the subscript means common mode, and a pair of differential sources. The D in the subscript here stands for differential. But I'm going to say that these two models are equivalent. In other words, the voltage here at this node is V sub 1, and the voltage here at this node is V sub 2, just like it was in the left model. Now let's force these models to be equal to one another. I want to find V sub Cm and V sub D in terms of our initial voltages, V1 and V2. This can very easily be done through the Kirchhoff voltage law. Let's just find the voltage between V1 and V2. We have two sources in this path, both of them V sub D over 2. This is just V sub D. Therefore, my differential voltage, in terms of the voltages on the left, is just V1 minus V2. Of course, that's what I expect. If it's differential, it should have something to do with the difference. Let's now write an equation for this voltage drop and this voltage drop. These two equations are equal to one another, and I can solve this equation for VCM. I now have definitions for the differential voltage and the common mode voltage at the input. If you look at the equation for the common mode voltage, you might just notice that it's the same as the equation for the average. It's just the average of the signals at V1 and V2. In a general amplifier, the output voltage will be some differential gain times the differential voltage plus the common mode gain times some common mode voltage. As I mentioned before, a good differential amplifier will only amplify the difference between the signals. The common mode gain, ideally, ought to be 0. So in a good amplifier, in a good differential amplifier that is, this term won't be present. We're going to include it though now in our analysis. Realistic amplifiers, though, usually have some common mode gain, even though we don't want it. How would we measure the common mode gain of a real amplifier? Here's a setup that we could potentially use. We could have a common signal and feed it to both terminals of an amplifier. Ideally, the output would be 0. If I measure something other than 0, that's a direct measurement of the gain. In other words, the common mode gain, ACM, equals the output voltage divided by the common mode input signal. How would we measure the differential gain? Well, to measure the differential gain, I would put one signal on one terminal, and then I would put its inverse on the other terminal. You might notice here that one of these voltage sources is upside down relative to the other one. The differential gain in such a setup would just be the output voltage divided by my input voltage V sub D. V sub D is just the voltage existing between these two terminals. Now I'd like to talk about the main topic of the video, the common mode rejection ratio. We know that a good differential amplifier will not amplify the average voltage shared between the two signals. It's going to reject the common mode voltage. What it means is that we want the common mode rejection ratio to be as large as possible. It's typically defined using a log scale. We want this number to be as large as possible because we want A sub Cm ideally to be as small as possible. Because we want a small number in the denominator, it means we want a large number overall. The common mode rejection ratio then gives us a metric or a way to characterize how good a differential amplifier is. If one differential amplifier has a larger common mode rejection ratio than another differential amplifier, we could say it's a better amplifier. Now I'd like to look at an op-amp in particular. An ideal op-amp is a very good differential amplifier. But of course, it's not perfect, and we'll talk about some of those imperfections in the upcoming videos. But for now, let's look at an ideal op-amp, and you can see that ideally, it has an infinite common mode rejection ratio. How do I know that? Well, if I look over here at the equation for the output, I can see that it has only an A sub D. There's no component for ACM. It's not there because it's 0. Some other characteristics of an ideal op-amp are firstly that it should have an infinite input impedance. If the input impedance is infinite, it means that there ought to be 0 current passing into either of these input pins. Secondly, it should have an infinite gain for the differential signal. A sub D, ideally, ought to be infinite. It should have 0 common mode gain, as we just talked about. It should also have 0 output impedance. The controlled source here is just the output voltage, and the resistor up here in the model would be 0 ohms. Finally, the op-amp should have all of these characteristics for any frequency. That is, it has infinite bandwidth. That's an ideal op-amp. Of course, a real op-amp is going to have all kinds of limitations. I've done some experiments with, for example, the LM741 op-amp. I know it's not ideal because this is what it looks like on the inside. It has all kinds of transistors in it. Each one of these transistors is going to have its own set of parasitics and limitations. So taken as a whole, they translate to several limitations of the ideal op-amp, but it turns out to be a really good amplifier nonetheless.